Hey guys, Mr. Carlos here. So it sounds like you are learning about something very important that photography or video could not exist without. Do you know what that is? It's light. So a little bird told me that you guys are learning about polarization or polarized glass, and I thought it would be cool to show you two pieces of equipment that I have available to me that may illustrate what you or what I think that you guys are studying. So here it is. It's two different kinds of filters. These filters are for the DSLR camera, and basically it's a metal ring with a screw ring and then a piece of glass. So this attaches to the front of the camera, and voila, it reduces the amount of light that it goes through the lens, and therefore it affects your exposure. Okay, so just really quickly on exposure. Exposure is how much light goes to make your image, and let's make a quick experiment about that right now. So I'm going to tap the center of the screen. I'm going to hold it to lock the focus, and I'm going to show you what overexposing your image looks like. This, way too much light, is almost completely white. Okay. And this is what underexposing your image looks like. Way too little light, we cannot almost see anything, so it's almost black. Right? So good exposure means that you have enough light to be able to see the lightest parts of your image, but also not losing the detail in the darker parts of your image. Okay? And that's where these two guys come in handy. Okay? Because we cannot always control the sky, or we cannot always control the light in our environment, but we can control the camera and how much light goes through the camera at a given point. So let's give this a try. I have two different kinds of lenses here, filters here. This first one is a fixed neutral density. So this one, let's see. I'm going to tap refocus over here. Okay, so now my focus is exactly right here, and I'm going to overexpose a little bit to show this. Okay, and now look at what happens. Okay, we've gone down a few stops in the exposure, right? We can almost see it like how it was originally. If I take it out, then the image is completely overexposed. This other filter is super cool, actually. This is two pieces of glass in the metal ring, and it also screws to the front of your lens. And because it's two pieces of glass, then we are able to move them this way, and that creates actually a pretty cool effect. So I'm going to focus on the center of the screen over here, and I'm going to actually leave it in the middle exposure, even though it's a little too bright. But I want to show you what this does, because it's pretty cool. So it goes like this. Okay. So this is a variable density. Okay, which means that I can change the density of the glass just by spinning it, spinning the ring. Okay, so this is the lightest point. I think that's a 2, and it goes up to a 10. Probably the 4 where we were before. 8, 10. Can't see a darn thing. Okay, I realized that outside I wasn't able to show you what the filter really looked like. So it's essentially this. Okay, and then this one, the variable density, has 2 rings. And do you see it rotating here? Now we should be able to see the wood again. Okay. Alright. Bye. Now, this is the experiential part. I know how to show it, and I know how it affects how it affects the camera. But Ms. Muge, what's happening here? Can you explain this for us?
Well, thank you very much, Mr. Carlos, for taking the time to share this mini lesson with us today. We really appreciate it. It was really cool to see your devices. They look pretty cool. And photography is fascinating to a physicist, obviously, because it's all about light and how you manipulate it. And the answer is yes, I should be able to explain it. So let's go. The first thing we need to understand is the difference between polarized and unpolarized light. We have an image given here to show how unpolarized light is modeled. Remember that electromagnetic waves are oscillations of the electric field vector. And for unpolarized light, the oscillation of the electric field vector takes place in only a single plane. Now, in unpolarized light, that electric field vector oscillation takes place in all dimensions. When light is polarized, however, we have that oscillation taking place in only one dimension. So a polarizing sheet or an polarizing lens is a device that allows electric field vector to oscillate in only one dimension. We have another image here to model how light can be polarized. For example, if this is polarized light after passing through this polarizing sheet, and there's another polarizing sheet, this light can continue to move through after the second polarizer. However, if light goes through one polarizer which has a vertical axis and it hits another polarizer which has a horizontal axis, it cannot get through that one. And this is when you saw it get really dark with the second lens that Mr. Carlos was showing us. So the definition of polarized light is light waves in which the electric field vector oscillations occur in only one plane is known as polarized light. There are other uses of polarization. There are several actually. Here are some examples for you to look up and read more into if you're interested. Go through this list. I find that second one pretty interesting actually because nature is fascinating. So if you're interested and if you have time, go for it. Research these things and find uses of polarization. Here's a simulation to show us unpolarized light, first polarizing filter, polarized light, second polarized filter, and the final intensity. So I'm showing one slit here after the first polarizer, and the angle here is the angle between this axis and that axis. So when the angle is 0, the two polarizers are actually aligned. Let's see what happens when I change the angle of the second one. I would like you to focus on the intensity, the amplitude of oscillations of the light that is shown after the second one. So I'm now changing the angle, and as I increase the angle, as it gets closer and closer to 90, you can see how little this intensity gets, and at 90 it actually becomes 0, and when I bring it back it reaches the same intensity it received. Okay, it's not as cool as what Mr. Carlos showed us, but I do have polarizing filters in the lab and I happen to have them with me at home. So I wanted to show you how they work with my own tools. And let's see that. I wanted to have a bright background, so I face my camera outside the window. That's the first polarizer sheet. And that's my second polarizer sheet. And I'm turning one of them, and you see when they're 90 degrees, there's zero intensity, and now back to zero, and I have full intensity back, and the same pattern when I go back. This is what was happening in Mr. Carlos's second gadget. I have the same image as before, but now there's one more added, and I can have this one and that one perpendicular to each other actually, and still get some intensity out by simply manipulating the middle one. Let's see how this works. So first I'm turning the middle one. Obviously when I reach 90, no intensity remains, so nothing to show. Back to zero. Do the same with the second one. When it's 90, nothing going out. But when I keep the middle one, say at 60 degrees, there's some intensity reduction here, yes, but when I move that to 90 degrees from the beginning, I actually see some intensity here, because what matters is the angle between the last two. So this one, because of the angle 60, reduces the intensity of the light, and then as this light approaches with that alignment to the third one, the angle between these two, which is now 30 degrees, determines how much of that intensity is allowed to get out of this last one. Let's explain polarization of light and Malus's law, which governs the mathematical relationship between intensity and the angular alignment of two or more polarizers. Now, I have drawn a ray of light here already. When light is unpolarized, the electric field vector is said to be oscillating in all planes. In other words, we can represent it as such. All of these directions of oscillations represent the direction of oscillation of the electric field vector. This is how we model unpolarized light. Let's label its intensity, because we're going to be looking for an intensity relationship when I add more polarizers. Let's call this IO. And now I'm going to place a polarizing filter in front of this. So that's my filter. And if that filter has a polarization axis aligned vertically, we represent it like that, which means only the oscillation of electric vector can remain on that alignment after passing through this polarizer, which means after passing through this polarizer, the oscillation of the electric field vector will only be in that axis. Now, once unpolarized light passes through the first polarizer, its intensity drops to half of the initial unpolarized intensity. So I'm going to label this one IO and call this 2IO for a reason I'm going to explain in a minute. Just remember that unpolarized light passing through one polarizer will always have its uncertainty reduced to half. Did I just say uncertainty? I think I did. Sorry, I meant to say intensity, not uncertainty, obviously. It happens. Moving on. Now that we have polarized light, let's put another polarizer in front of this. So here's my second polarizer, which we also call the analyzer. Let's say the axis of polarization of this second one is aligned with the first one. In that case, nothing will change because this light is already polarized in the vertical axis. So if the second one also has its axis with 0 degrees to the first one, then nothing will change in terms of the intensity. The light that is here can pass through with the same intensity and out. However, if we rotate this second polarizer and align its axis as such, there's going to be a change in the intensity of the outgoing light after the second polarizer. And that depends on the angle of the axis of polarization of the two polarizers, which I'm going to show on the diagram as such. That's the angle I'm talking about. This is the axis of polarization of the first one. That's the axis of polarization of the second one. The angle between those two axes is the angle that I'm interested in, which determines how much intensity the outgoing ray will have. But before I give you that, I will show the polarization of the outgoing light. Since this is the alignment of the polarization axis for the second one, only light that oscillates in that dimension can leave, which means my outgoing ray will have that alignment for its polarization. And let's label its intensity I. And Malus's law gives us the relationship between the I and this IO, which is given as such. So this is given in the data booklet. I equals IO cosine squared theta. And this is exactly why I wanted to keep this intensity IO over here, because the formula that we have relates the intensity of polarized light to the light that is polarized after a second polarizer. So the intensity of the unpolarized light initially would be double the intensity after the first polarizer. So I kept this IO, and that is I, and that's the relationship depending on the angle between the polarization axes of the two polarizers. Now, as you can tell from the formula, if this angle is 90 degrees, cosine of 90 would be 0. So the final intensity would be 0 no matter what this intensity or that intensity is. Which is why what we saw in my demonstration and in Mr. Carlos's video, when the angle between the two polarizers reaches 90 degrees, it appears completely dark. And that is because there's no intensity left to leave this second polarizer. Now at this point, I have two reminders for you. You might find in past papers questions that mention Brewster's angle and optically active surfaces. It's very important that you know that these two are out. So don't get caught on those questions. And another reminder that I'd like to give you is to always check whether the incident light is polarized or not. Some questions will give you incident light which is already polarized. So you have to check for its axis of polarization and calculate the intensity after the first polarizer that's given. And if there's a second one, you have to apply the Malus's law again. So that brings me to my final reminder. If there is another polarizer here, then the mathematical relationship of intensities always works for the pairs of. So I've modified this diagram to show you what that looks like. Let's say this is the first polarizer, 2I1 original intensity reducing to I1 after the first polarizer, I2 after the second polarizer, and I3 after the third polarizer. Well, I know I1 is half of the original, so I'll use Malus's law to relate I1, I2, and I3. I2 would be I1 cosine squared theta 1 right here between I1 and I2. And then once you calculate I2, you can now calculate I3 using the angle between I2 and I3, which is theta 2 in my diagram.
A final word on polarization. Polarization is a property of light only. Sound waves cannot be polarized simply because of the nature of the wave,
which is not traveling in vectors that are oscillating on all dimensions, so there is nothing to polarize in a sound wave. That's it for this lesson. These are your homework questions, explanations on my next video. See you later. This is still question 4. And that's the rest of question 5.